I want to say some more things about the chain rule. I will refresh our memory. My screen is all crazy. Sorry. The formula for the chain rule. The chain rule is about the derivative of a thing inside a thing, right? And it says you take the derivative of the outer function with the same thing plugged into the inner function, and then times the derivative of the inner function. All right, that's the formula for the chain rule. I would suggest that you remember it just like I just said, not so much like memorizing the F's and the G's, although you can if you want to. When I do the chain rule, I don't really think of it in terms of the F's and the G's. I think of it in terms of there's a function on the outside and another function on the inside. You do the derivative on the outside first, leaving the same thing on the inside, and then you multiply times the derivative of the inside. So, simple examples. How about what's the derivative of cosine cubed of x? All right. This one I think would be helpful. It's get my pointer out of there. In my opinion, it's basically always helpful to write this like this, cosine of x cubed. That's what cosine cubed of x means. I am basically always going to rewrite, whenever you see cosine squared or cosine cubed or whatever, is that. And now, doing the derivative here, the chain rule says I do the derivative of the outside part first, and in this case the outside part is the power of 3. So I'm going to do the derivative of that first, which means bring the 3 down and then decrease the power to a 2. That's doing the derivative of the outside part, leaving the same thing on the inside for now, and then separately you multiply times the derivative of the inside. Anyone remember the derivative of cosine is? Somebody shout it out. Negative sign. Yes, mumble it out. Thank you. All right, great. And that's the derivative of cosine cubed. It's that. All right, this is the chain rule. Here's a fancier one. How about the derivative of square root of x sine x? Can we do that? I think it would be helpful to rewrite this. Anyone have a suggestion? How should I rewrite that? Yeah, with a fractional exponent, right? Instead of the square root, I'm going to write x sine x to the power 1/2. It's basically always better in this class, just because of the way the derivative rules work. It's basically always better to write it with the 1/2 power rather than the square root sign. All right, I didn't do the derivative yet, but now I'm going to do it. This is the chain rule again. I have a thing on the outside, which is the 1/2 power. The thing on the inside, which is x times sine x. So I do the derivative of the thing on the outside first. It looks like that, right? The power comes down and then decreases by 1. Leaving the same thing on the inside. And then I go times the derivative of the inside. And what should I do for the derivative of the inside? Cosine x? Yes, I hear some people say, you got to do the product rule. Am I blowing your minds? Can you have a product rule inside a chain rule? Yeah, you can. It's not all that mind-blowing. If the thing inside the parentheses is a product, then when it comes time to take the derivative on the inside, you got to do the product rule. So the product rule, I hope you remember, my product is like this, right? These are the two pieces. X is the first part, and sine x is the second part. So the product rule says I go the first part like it is, times the derivative of the second part is cosine x, plus the second part like it is, which is sine x, times the derivative of the first part, which will be 1. That's it. All right, this is a product rule inside a chain rule. You can also have a chain rule inside a product rule, or anything inside anything, right? Any thoughts about that? No. I wouldn't try to simplify this. I mean, I suppose you probably could rewrite some parts of that, but I don't care about that. This is generally, when I ask you to find the derivative of something, I expect you to take the derivative and then, drop the mic and back away. Like this, that is the derivative, what I wrote there. It's true you could write that in some other ways if you wanted to, but if I ask you to find the derivative, just find the derivative. You don't have to simplify unless I tell you to simplify it. Right? Excellent. So this is all basically what we did last time. I would like to talk about another way of writing the chain rule, which you may or may not have seen. Another form of the chain rule. Another form of the chain rule. This is the, the way that I wrote it before was, so this is not another form, this is just how we write. I don't need to write it again. It's the one that I wrote before is the one which uses like the f primes, right? What if instead you want to write the derivative in like the dy over dx form? So that's called the Leibniz form, because this is the way that Leibniz, one of the inventors of calculus, wrote it. The Leibniz form, that is in terms of like x's and y's, all right? Remember the scenario for the chain rule is when you have one thing which depends on another thing, but then that other thing also depends on another thing. That's how you get the thing inside of a thing, right? So the scenario when you want to use the chain rule is something like, let's say that y depends on some other variable u, and this other variable u depends on x. All right? So I have the one thing which depends on another thing, but then that other thing is actually depending on yet another thing. All right? And then what are the derivatives of various things? Well, we could discuss then, we have, of course, dy du. If y depends on u, you can talk about this derivative. This is called the rate of change. Do you mind if I say ROC? The rate of change, the derivative, right, of y. What this is called is with respect to u, meaning this is a measurement of how y is changing when you change u a little bit, right? Of course, u is depending on x, so we could also talk about du dx. This is the rate of change of u with respect to x, right? Because u depends on x. But it is also true, because of the setup here, that y in some roundabout way does depend on x, because y depends on u, and u itself also depends on x. So also we have dy dx actually makes sense, although it's a more sort of an indirect thing. Y depends on u, and u depends on x. That means in some way y does depend on x. This is the rate of change of y with respect to x, right? And the Leibniz rule is sometimes called, it's really the same as the chain rule, but it's the way that Leibniz wrote it, is a formula relating these three things. In terms of the other form of the chain rule, this is kind of the derivative of the big thing inside of a thing, because this is how y has a sort of a u inside of it, and the x is inside of that. How this depends on x is kind of the derivative of the thing inside a thing. And then these two are the other two parts. Anyway, I'll tell you the form that the chain rule takes in this context. It's a cute-looking formula. The way that y depends on x is just equal to the way that y depends on u times the way that u depends on x. That's all there is to it. All right? This is sometimes called the Leibniz rule. It's just the chain rule, but written in a slightly different way. And in the language that we've been using in the past, like this first thing represents sort of the derivative of the outside thing, and then this represents the derivative of the inside thing. I'm writing them differently. And this is actually one of the reasons why we write the derivative as if it were a fraction. Everybody knows this dy over dx is not actually a fraction, but one of the reasons why we write it in such a way that it looks like a fraction is because of this formula. Because in this formula, you could imagine that you're canceling the du's in this fraction, and what you end up with is dy over dx, which is, I imagine this is why Leibniz fancied writing the derivative as if it looks like a fraction, even though it's not a fraction. It does behave kind of like a fraction in terms of the chain rule at least. All right? So I want to try some examples of this form of the chain rule. This is sort of useful in a lot of applied settings. They like to write derivatives in this way. So here's an example. Let's say sorry, my screen is all wacky today. Let's say I'm pumping up a balloon, a spherical balloon. A spherical balloon, and let's say the radius obeys this formula. R of t is 4 minus 3 over t. So this formula describes what the radius is over time, all right? If you think about it here, as the t grows larger and larger, the radius is approaching 4, but it's not 4 when you start. All right, so let's say this is a formula for the radius over time. I would like to know, so your job, give a formula for dv dt, where v is the volume, all right? So I told you the way that the radius is changing over time, and I would like to know how fast the volume is changing at various times, all right? This is the rate of change of the volume. Rate of change of the volume. All right? And I hope you can see the setup here is that, I told you what the radius is over time. You could, if you want to, find the derivative of that. That would tell you how fast the radius is changing. But I'm asking you about the volume, and the volume depends on the radius, and the radius itself is depending on time. So that's the sort of, this depends on that depends on that setup. I have the volume, the radius, and the time. All right? So what I'm going to do is make a formula for each. So my formulas, well, I have a formula for r, which I already told you, 3 minus 3 over t. And also a formula for the volume of a sphere. Now, this is not something I especially expect you all to have memorized. Anybody happen to know this? Any masters of formulas, geometry formulas? It's got a pi in it. There is, she said, 4/3. I think that's exactly what she said. Yeah. Anyone remember the rest of it? There's a 4/3. There's a pi. It goes right here. And there's an r cubed. Great job. I say it like Dora. She asks a question and just assumes that everybody knew the answer. 4/3 pi r cubed is the formula for the volume of a sphere. All right. Like I said, I don't expect everybody to know that. I would expect you to be able to look that up if you have to. All right. So that's the formula for the volume of the sphere. And according to the chain rule, I asked you to find dv dt. And dv dt, according to the chain rule, it must equal dv dr times dr dt, right? And I can find each of those derivatives by just, taking the derivative of those two formulas. So, I guess let's do it. What, we'll just do each of those derivatives. So what is dr dt? That will be, take the derivative right here, considering t as the variable. And want to tell me what would you get from that? I suppose if I were preparing to take the derivative here, it would be more convenient to write it like this, right? The division by t, instead of 3 over t, that's the same as 3 times t to the minus 1, which is a better, easier thing to take the derivative of. What do you say? I'm doing dr dt here.
Oh, sorry.
I think you're doing the other one. What do you think? 3 over t squared. Yeah, if you go right here and take the derivative using t as the variable, I would say you get, most obviously, plus t, 3t to the minus 2, right? Which she said is 3 over t squared. Although, would you mind if I just leave it like this? All right? Excellent. That's dr dt. What about dv dr? That means you take the derivative of the volume formula using r as the variable right here. And this is, I think, what you said before. What did you say?
12 squared.
I almost agree. I don't quite like the 12, or maybe, did you perhaps forget about that?
4.
Yeah, just 4. This exponent is going to come down, multiply onto the coefficient, so it's going to be 4/3 pi, but then times 3. We'll cancel the denominator of 3, and I get 4 pi r squared, right? That is taking the derivative right here, using r as the variable. Yeah, pi, remember, is just a number, so all of this is really just a big constant. And a constant coefficient always stays like it is when you take the derivative. Yep. Okay, so we're pretty much done here. The whole question was, remember, give a formula for dv dt. So I'm going to just combine all this business together, right? I said before, the chain rule says dv dt is just the product of those two things. So dv dt is, it's dv dr times dr dt, and we just figured out what each of those things were. It's 4 pi r squared times 3t to the minus 2. Right? There's one thing about this that I don't really like, and that is when I say dv dt, it means the derivative of v as it depends on t. What I don't like about this is it has an r in it, which is a little weird. Like if I'm trying to ask you, how does what this means, how does the volume change in terms of the time? Really, you should just give everything in terms of the time. There shouldn't also be r's in here. This is an easy thing to fix because already, all the way at the top here, we already have a formula for r in terms of t. So to get this all in terms of t, if I wanted to do this on a test or something, I would specifically say, give your answer only in terms of t, no r's. You just replace this r. It said r squared down there. Sorry, I keep scrolling up and down. It said r squared. I'm just going to replace r by that, 4 minus 3t to the minus 1. So my final answer is dv dt is 4 pi, and then this r becomes 4 minus 3t to the minus 1 squared times 3t to the minus 2. All right, and this is my final answer. Like I said before, you could try to simplify that, I guess, but I wouldn't say there's any reason to simplify. It wouldn't be pretty either. You'd have to actually do the FOIL here and then recombine everything. I'm not into that. All right, any thoughts about that? This is the Leibniz form of the chain rule. All right, you're going to see some of this on the homeworks, I'm sure. That is about all I wanted to say about the chain rule. We have plenty of time left. Are you waiting for me at any moment to say, hey, let's just leave for the break? Not happening. We got plenty of time. All right, I want to go on to the next section. This is called... Oops. Did I just make it worse by saying that? I don't know. I'm having a great day. I feel... Oftentimes, I don't want to be here either right before break, but I'm actually in a good mood today. Implicit differentiation is the next section in the book. This is something that I don't know if, I know most of you folks have done the derivative before in high school. I don't know about this. This is like a more obscure topic as far as high school goes. Maybe you did this in high school, I don't know. Implicit differentiation is about finding slopes along weird curves that are not even functions. And we're going to see some very weird curves today. Finding slopes along weird curves that aren't necessarily functions. Although, of course, you can do this for functions. It's just not usually necessary if it is a function. Aren't necessarily I think I spelled that wrong. Function. All right. I'm referring to something like a circle, right? I mean something that you know the equation of, but it doesn't technically make a function. Something like a circle. For example, if I have a circle like this, let's say a circle with radius 3, those are unevenly spaced. A circle with radius 3 like that. How about, can you tell me what the slope is right there, where x equals 1 and y equals something? What is the slope right there? All right. How about the slope at the top part, come on, of the circle, radius 3, when x equals 1. All right? Can I find that slope? This is not a function, right? Because that shape doesn't satisfy the vertical line test. Anyone happen to remember, this I probably would expect you to know. What's the formula for the circle with radius 3? Remember this? The formula for a circle in general? Yeah? This is the area of a circle. I want like actually the equation which gives you the graph of the circle. I appreciate the formula knowledge. Anyone recall this? Yeah? Yeah, so I would write it this way. X squared plus y squared equals r squared is the general formula for, so this is the formula for a graph of a circle where r is the radius. So in this specific case, I said the radius is going to be 3, so it's this. What we're going to talk about in this section is any kind of formula which has just some weird mixture of x's and y's, right? One reason why this is not a function is because it's not even solved for y here. A function is always y equals whatever in terms of x, right? But here the formula is just some strange combination of x's and y's jumbled together. Even such a thing, you can find slopes of it. You can take the derivative using, in that case, it's called the implicit derivative. All right. The reason is because here, it's not solved for y, which is a problem, but you have to do it with the implicit derivative. Not solved for y, so I'm just going to try and give you the language here. Y is not explicitly given in terms of x, right? Instead, y and x are kind of mixed together. You could say y is defined by x kind of implicitly. That's why it's called the implicit derivative. In a formula like this, y is not explicitly given. Y is implicitly determined by x. That's just where the word implicit derivative comes from. All right. The word explicit, you know, people generally, when they say that word, they mean like swear words and things like that. But explicit just means like being super specific about what you're saying, right? That's explicit. So, you know, something like y equals x squared plus 5. This is an explicit equation, explicit content, right? I'm going to have to flag this YouTube video because of that explicit equation. This is called an implicit equation because it doesn't have the variable solved. All right, anyway, the moral of what we're talking about today is you can take the derivative even of an implicit equation. So it's called the implicit derivative. We can take the derivative of an implicit formula. That is something which has a bunch of x's and y's just kind of jumbled together. And the way to do this is you take the derivative. I'm going to tell you how to do it. It's not really hard to do. You just have to know what you're doing. Take the derivative of everything on both sides of the equation, right? Such a formula always has it actually has two sides to it. It's not just a function equals some stuff. It's got two sides of an equal sign. You take the derivative of everything on both sides. And then, you treat x like a variable. And so, for example, the derivative of x becomes 1. But y is a special thing. And when you take the derivative of y, what you get is dy dx, right? That means the derivative of y. So take the derivative of everything on both sides. And I will say, I didn't need to put a comma there. With respect to x, that is thinking of x as the variable. And the derivative of y becomes dy dx. Like that means the derivative of y, right? And anyway, this is how you do the implicit derivative. All right, let's just do this simple example. So let's find dy dx. See if we can do it. This will give me the slope along the circle at any point. That's the idea, at least. What we do is we go through the entire thing and take the derivative of everything on both sides. So the derivative of everything on both sides. On the left side, actually, could I do the right side first? What's the derivative of 9? 0. A constant always gives you 0 in the derivative. On the left side, the derivative of x squared is 2x, yeah, thank you. Plus the derivative of y squared. Here's the only tricky bit, and it's not really very tricky. What I see here, I think of like a chain rule. This is slightly weird, but you think of y is the inside function, and the squaring, of course, is the outside. So I'm going to do the derivative on the outside first, which is you bring the 2 down, you keep the inside like it is, which is a y, and you decrease the power by 1. And then, because of the chain rule, I go times the derivative of the inside. And what is the derivative of the inside? The inside is just y, so the derivative of the inside is dy dx. And this is my derivative. And now we can solve for dy dx. Because I mean, that was the point of this. I wanted you to find dy dx. So now solve for dy dx. What you get, I guess I would subtract the 2x onto the other side of the equation. It says 2y, that's y to the 1, not a y prime. 2y times dy dx equals negative 2x, right? The 2's can cancel, and I divide by y, and it looks like dy dx equals negative x over y. That's the derivative, the implicit derivative. All right? Take the derivative of everything. Let me just summarize again how that worked. You take the derivative of everything, both sides of the equation, and you just have to remember, the only trick is right here. Whenever I took the derivative of something involving y, remember this used to be a y squared, I turned it into 2y. You just have to remember to multiply by dy dx. So I take the derivative of everything, and whenever we get to a y, you also, you take the derivative, but you also multiply by dy dx. Really, this is because of the chain rule, although you don't really have to think of it as a chain rule. In my opinion, I just think of it as, it used to be a y squared here. Take the derivative of y squared gives me a 2y, and then I multiply by dy dx. Sorry, I scrolled past. Yeah, if it was dx over dy, then you would treat y like the variable, and this would just stay as a 2y, and this would become 2x times dx over dy. Well, that's pretty weird. It's not usually going to happen. It's only one dx over dy. Yeah. All right. Can we answer the specific? One thing I want to point out is you should expect your answer. The original function was not explicit in terms of y, in terms of x. It had a mixture of x's and y's. When you do the implicit derivative, you should expect your answer to also have a mixture of x's and y's. And sometimes this is inconvenient, but I will just say the answer will have a mixture of x's and y's. All right? You shouldn't be surprised if that happens in your answer. But anyway, can we try to answer the specific question that I asked, which was in the circle of radius 3, I tried to to make a better looking circle this time, but I didn't really. If you take the tangent line where x equals 1, all right? So can I do specifically, oh, come on. When x equal 1, what's the slope right there? I mean, just eyeballing it, it looks like negative something. I don't know. Down 1 over 2, so maybe negative a half. I mean, this picture is not accurate at all, but maybe this slope is negative a half. I don't know. Can we try and do this? Specifically when x equals negative 1. So remember the formula that we came up with was dy dx equals minus x over y, right? And I just want to plug in x equal 1. Unfortunately, you also have to plug in y here, which is not great, I guess. Like it's maybe not obvious what the y even is here. So I'm going to use x equal 1. For y, I guess the best we can do is you can figure out what is the y when the x equals 1 just using the formula for the circle, right? The formula we started with. For y, I'm going to do, x squared plus y squared equals 9. That was our original formula. But then if I plug in x equal 1, I'll be able to solve for y. That will give me the y value, which corresponds to the x value of 1. So it's 1 plus y squared equals 9. I want to know what's the y value when the x is 1. I guess we could subtract 1 here. Y squared equals 8. And so y is plus or minus 8. I got two answers here. Which one do I want, the plus 8 or the minus 8? The plus 8, yeah, why do you say that? Yeah, just because I said so on the picture, I want this point up here. I hope you agree. There are two y values when x equals 1. That's why I got two answers. I want the positive one just because I said so. So I'm going to use x equal 1, y equals square root of 8, right? And plug that into my slope formula, and that'll do it. So dy dx is minus 1 over root 8. And this I put into my calculator. This is about negative 0.35 if you run those numbers in the calculator. Which is vaguely what I expected, right? I mean, I said it was something like 1/2. It's more like negative 1/3, but close enough, right? Any thoughts about that? This is the implicit derivative. You can use it to find the slope along a curve, even if that curve is not a real function, even if it's just some kind of weird mixture of x's and y's. All right? I said we could do this to look at some weird curves. I got some weird examples here. I got just two examples, and then we can go. How about that? One is one for you guys to try. I'm going to do one, then you guys can do one. Anyway, let's see if I can find the slope of this weird curve. Sine of xy equals sine of x plus sine of y. All right? Anyone happen to know what that shape looks like when you graph it? I'm telling you, this is crazy. I want to find the slope. I'll show you the picture in a moment. Find the slope at x equals pi and y equals 0. This is actually a point on this curve. I don't know if can a normal, like a TI calculator, graph something like this? Probably can somehow, although like the standard graphing thing is always supposed to be solved for y. Anyway, my fancy graphing app here, my fancy free graphing app, check it out. It has an x and a y, so I'm going to say sine of x times y equals, I really like this picture. Sine of x, that's crazy, but that's not even what we're doing here. Sine of x plus sine of y. Ready for this? Yeah! How do you like that? Nice. This isn't actually just one curve. You can see like these guys are like its own little thing there. But anyway, you can use the implicit derivative to find the slope along any, like, what's the slope, right here? You can do that using the implicit derivative. I specifically said I would like the slope when y equals 0 and x equals pi. That would be right here. You can see it goes through pi. The x value in the x-intercept is going to be pi there. So this slope there, again, it looks something like -0.5, I guess. It goes maybe down 1 and over 2. So something like -0.5 is what I want to see. All right. Being able to see this picture is no help. Doing the problem actually has nothing to do with looking at the graph, but I just thought that's I like the looks of that. Okay, let's see if we can do it. So this is my formula here, and I am going to take the implicit derivative. That means you go across the whole formula and take the derivative of everything on both sides of the equation. And whenever you see a y, you're going to multiply by dy dx. So, well, let's just start on the left side. Sine of x times y. This, we have to use the chain rule because I have a thing inside of a thing, right? X times y is inside of the sine. So first I do the derivative on the outside. The sine becomes a cosine. So it's cosine of x times y times, and now the derivative of the inside. The derivative of x times y, what do I got to do for that? This is a product rule, because the inside there, x times y, is x times y. So I do the product rule. It is the first thing, which is x, times the derivative of the second thing. The derivative of y is, what do I do for derivative of y? It is dy over dx, yeah. All right, and then plus the second part, which was y, times the derivative of x, which is 1. All right? So that is the derivative of the left side. Equal. What's the derivative of equal? The answer is equal. That was a joke, I guess. I don't know. That was just a weird thing to say, I guess. What is the derivative of sine x? Cosine x, yeah. And then the derivative of sine y, what do you think? Yes, cosine y dy dx. Great. You just take the derivative as usual, but anytime you take the derivative of y, you have to multiply by dy dx. All right, excellent. Our next step would be to solve for dy dx and then plug in whatever values we want. Now, in this case, I would say, just looking at that, I don't really want to solve for dy dx in there because it's so weird. Rather than solving and then plugging in, let me just say, we want to solve for dy dx, then plug in x equal pi, y equals 0, right? It's almost always easier to plug the values in first and then solve for dy dx, right? Once I plug in x equals pi and y equals 0, a lot of this will simplify itself, and then it will be much easier to solve. So actually, don't do it in that order. We should plug first, then solve, all right? This is going to be easier. So I will plug in x equal pi and y equals 0. It says cosine of pi times 0 times pi dy dx plus 0 times 1 equals cosine 0 plus cosine, sorry, that's a pi, cosine pi. I'm plugging in x equals pi and y equals 0. Cosine 0 dy dx, like so. All right? A lot of this will simplify. First off, I have cosine of 0, and then we have pi dy dx. 0 times 1 is 0. Equals, on the right side, cosine pi plus cosine 0 dy dx. And what is cosine 0? Anybody? 1. Yeah, cosine of 0 is 1. Remember the graph of cosine looks like this, right? where cosine of 0 is 1, cosine of pi is negative 1. And so, plugging that stuff in, this is 1 pi dy dx equals 1. No, cosine of pi is negative 1. Negative 1 plus cosine of 0 is 1. All right? Can we solve that for dy dx? I think so. The left side is just pi dy dx. The right side is minus 1 plus dy dx. How would I solve this for dy dx? There's no tricks anymore. This is like, I guess, just ordinary algebra at this point. What would you do to solve for dy dx? Yeah? Yeah, put everything that has a dy dx on one side. So maybe I'll put them all on the left side. Subtract the one which is on the right, subtract it over. So it'll say pi dy dx minus dy dx equals negative 1. And then he said factor it out. I think what he meant was this. Dy dx pi minus 1 equals negative 1. And then you can divide both sides by pi minus 1. And that's what it is. Negative 1 over pi minus 1. And this I put into my calculator. Remember, pi, actually, I don't think I did put this in my calculator. If you believe like pi is basically 3, then on the bottom, this looks like 1/2, right? Negative 1/2. Because pi minus 1 on the bottom is close to 2. So this is actually close to minus 1/2, which again is what I predicted that it would be based on the picture. Right? Any thoughts about that? Remember, we were finding the slope at this point right here. Negative 1/2 looks reasonable to me. Okay? Yeah, you want to see this one. Right? Excellent. I got one for you all to try in our remaining 15 minutes. I don't think it'll take that long. All right, let's try. I'm going to do the same idea. Find the slope. This one's a little easier because it doesn't have the trig stuff in it. Find the slope of this formula. X squared minus xy minus y squared equals 1 at the point 2, 1. All right, see if you can do it. Just for fun, I will graph this after you copy it down, just so you can see. Although it really doesn't matter what it looks like in order for you to answer the question. You don't have to look at the graph. That's what it looks like. A bit less interesting than the last previous one. let's go over this. I don't know if you finished yet, but everybody wants to leave. Take the implicit derivative. This is what I got. The first part, x squared, just becomes 2x. The middle part, x times y, you have to do the product rule on that. And I got x times dy dx plus y times 1. Make sure you put parentheses around that thing, because you're going to have to distribute this minus sign here. And then I got minus y squared. Y squared becomes 2y dy dx. And equals 0. It should be on the other side. All right. I hope everybody got that for the derivative. And now I just, I'm almost done, I guess. I'm going to plug the values in. Plug in 2 and 1. And then solve for dy dx, right? Or you could solve for dy dx first. That's more complicated. I'm going to plug x equals 2, y equals 1, and then solve for dy dx, right? Let's do it. I got 2 times 2 minus 2 dy dx minus 1 minus 2 times dy dx. I distributed the minus sign in the middle there. And that would be 4 minus 2. Would you mind if I write y prime? I find that a little nicer. Minus 1 minus 2 y prime equals 0. Y prime here. Put all my y primes on the right side. There's negative 4 of them. I add them over and there will be 4 y prime. And over here there's 3. So y prime is 3/4. That's the slope at that point. Can I see if that looks reasonable on the picture? This is, anyone know the name of this shape? This is a hyperbola. Anyway, the point was right here, 2 comma 1, and I said 3/4. Did I? 3/4. That means up 3 and over 4. I can't make my dot on the picture, but looks reasonable, right? Sorry, you want to see this again. All right, that'll do it. I hope you all have a good break. Thank you for your continued attention. Late on a Friday afternoon. Thanks, you do.